Welcome to Frank Stajano Explains and to this Algorithms Extra video on Euclid's algorithm. We could in fact call it an Algorithms Extra stroke Discrete Maths Extra because you should have seen Euclid's algorithm in the Discrete Maths course last term. I believe, however, that if you've seen it, it would have been only presented through an algebraic presentation, and personally, I don't really own the algorithm when it's explained in that way, and to really understand what goes on, I need to have a more visual explanation. And so I want to introduce Euclid's algorithm for finding the greatest common divisor of two integers using a geometric representation. This algorithm is worth studying in our course because it's arguably one of the earliest descriptions of a non-trivial computational algorithm that exists in the literature. This goes back to about 300 BC. So the algorithm is, as we said, for finding the greatest common divisor between two natural numbers. And the way we are going to think about it is not in terms of divisibility, but in terms of geometry and surfaces. And these two numbers are going to be the sides of a rectangle, which will therefore have integer lengths. And so this rectangle is the wall of your bathroom, which you want to tile. And you want to tile it with square tiles that fit exactly from one edge to the other of the rectangle. And you want to use the largest possible square tiles that you can fit. So if you do manage to tile your rectangle with square tiles, then clearly the side of the square is a divisor of both the length of the long side and the length of the short side. If these tiles are the largest possible square tiles, then by definition the side of the tile is the greatest common divisor of the long side and the short side of your rectangle. So our job is simply to find what is this largest possible tile. And let me draw a rectangle so that we can see what's going on. I've made a rectangle, and what I'm going to do to it is fill it with the largest possible square tiles that I could put in there, which are the size of its small side. Well, I could fit 3 of these big red square tiles in there, and then there's a leftover piece. This leftover piece is also a rectangle with integer sides, because I've only subtracted integer stuff from integers that I began with. So I'm going to use the same procedure. I'm going to fill it with the largest square tiles I can. And my hope is that I would get to a point where the square tiles exactly match the rectangle I need to cover. But if I'm unlucky, as happened in the case of red, I will be left with some extra that I still need to cover with smaller tiles. I'm guaranteed that I will stop at some point because I said the sides were integers, so in the worst case I will get to a stage where leftover rectangle is only 1 unit thin, and then 1 by 1 tiles will fill it up exactly. So let's see what happens here. I could fit 3 blue squares, and I'm still left with a small leftover piece. And so I'm going to go for even smaller squares to try and fill that up. So now, of course, my drawing is very imprecise, and so I can to some extent make it up whether I hit the boundary exactly or not. But let's pretend that I was able to exactly fit 4 of these green tiles in the space that remained. Once I hit the case where one of my tiles completely fills exactly the leftover rectangle, then I have found my tile that works for the whole thing, because this green tile, if it fits that space exactly, then clearly it is also able to tile the blue square, because this is the side of the blue square, and the side of the blue square is exactly divided by the green square, and since the blue square is a square, this side is the same length, and therefore it would also take 4 green squares, and so this thing is a 4 by 4 tiled green tiles over here, and the same for this one, same for this one. And this is an integer number of green tiles, this is an integer number of green tiles, this one too, and this too, 1. And so this is an integer number of green tiles, and so is this one, which is the same length, and so on. And so basically every larger square that I have used is also going to be divisible by the green square, and so the green square will perfectly tile the whole rectangle that I have. And so that's the visual intuition as to why Euclid's algorithm actually works. You repeatedly exercise this operation of having a long side expressed as the short side times a quotient, which is the number of large tiles I managed to fit in, plus some remainder. So the long side is equal to the short side, which is the side of this square, times the number of squares q plus this remainder. And if the remainder is not 0, then I repeat the operation by saying that the long side is now the short side, and the short side is now the remainder, and then I go back and do the same until the remainder gets to 0. So if I were to write this as a pseudocode algorithm, what would I write? I would write that so here I have written out divide and conquer pseudocode recursive version of Euclid's algorithm, where I get my rectangle with a long and short side, and I try to fit in the short side as many times as possible, and what's left over is the remainder. Remainder equals long mod short. If there's no such remainder, then I have found my GCD, which is the short side that I used, which divided the long side exactly. And if there is a remainder instead, I repeat the procedure by again taking here the short side of the original as the new long and the remainder as the new short, and then I rerun the same thing again on the new long and short. Now this, as you can see, is a tailed recursive function, so I can express it as an iterative function simply by deleting that recursive call and replacing this by loop forever. And forever is not really forever, because I get out of it when the remainder is 0, and then I just return short. So this is an iterative version of the GCD according to Euclid, and this is, as I said earlier, one of the earliest recorded non-trivial computational algorithms. In fact, when Euclid defined it, he was doing it using repeated subtraction instead of division. So it's maybe slightly longer, more operations, but simpler operations. And I find this explanation lets me understand much more immediately why this procedure here actually gives me the GCD than if I just have this pseudocode and I work on reasoning on divisibility of integers, which of course is all true. So this isn't what I presented here isn't quite a proof, but it gives me a much greater confidence that the algorithm works, at least for how I reason. So if that helped you too and you liked it, then please make sure to hit the thumbs up button. Thank you.